Okay, so that will be the last theoretical bit of our kind of run through machine learning, because and we're going to talk about the neural networks and a little bit and kind of like very basic ideas of them. And we're only going to talk about, as I mentioned to you, what is called the fully connected or dense neural networks, and a little bit about convolutional neural networks. And we're not going to talk about fancy transformers and how ChatGPT works and things like this, because that requires, you know, a little course in machine learning of itself. But the idea is like, you know, at least you get something. And those of you who are interested and who want to understand, you know, how neural networks which can handle, you know, sequences of words or numbers, and the ChatGPT is one of those networks which can handle the sequences of words in the intelligible or quasi-intelligible way. Working, you can kind of take it from here and study by yourself. As I mentioned to you yesterday, there is zillion resources online. It's literally, you know, it's not a question of some secret knowledge which is being held and hidden from everybody. There are hundreds of courses for every taste of the lecturer, every taste of level of the material. Okay, so but let's go to the neural networks, and let's do a little bit of historical dive into the neural networks, which might be for some of you it might be a little boring, but it's useful to know where it's all coming from. So the first quasi-neural network is called the perceptron, and that was invented by the McCulloch and Pitts, and it was a model of what is called the biological neuron. So kind of like they were trying to figure out how to make, you know, the artificial neuron and to build the brain, because at that instance in 1943 it was still unclear, you know, how to build, you know, people didn't know about the building of the computers as the devices, and there was mainly two approaches which people were exploring, kind of two mainstream approaches. One was the digital approach which we have now, where, you know, we have a separate computer CPU, where you have a separate memory and you transfer instructions and things like this, or you have a brain-like structures, and that's why the perceptron as the model was invented to mimic the biological neuron. Because in these cases, you know, the computation are done by the structures which are having like memory and CPU together in one, so to say, kind of in one system. And it's a slightly different ways of calculation. And these kind of ways of calculations are now revisited for some other type of calculation, which are called neuromorphic computing. Okay, but in 1943, this perceptron model was suggested. Afterwards, there was a little implementation of it by the Rosenblatt, and afterwards, what happens that the Minsky and Papert, they have shown that the perceptrons are such a poor models that they cannot even learn what is called the XOR function. And the XOR function is just, you know, it's a data set which is consists of the data which is two-dimensional in the simplest case, yes, and it could be, you know, positive positive, positive negative, negative positive, and negative negative, and of course positive positive and negative negative is one class, positive negative and negative positive is a different class, because this is just a logical XOR function. And of course neural networks can learn this pattern, but, you know, perceptron was not good enough, simple perceptron as it was considered. Okay, so, and there was a little bit of what is called this AI winter, you know, when people were a little bit disappointed in AI in general. But afterwards, in the end of 80s, there was some developments. There was a convolutional neural networks was presented by the Jan LeCun. Afterwards, there was the LSTM architecture proposed, which allows you to do the sequences of words or sequences of numbers to address the time series and things like this. Afterwards, there was implementation of the convolutional neural networks on the MNIST data set, and that was already interesting because in 1998, it was a human level performance on the handwritten digit recognition was achieved. That is interesting, but that was not a breakthrough. The real breakthrough, when the people begin to take neural networks extremely seriously happens in 2012, and there is a standard ImageNet competition, which already is not happening because the problem is solved, or kind of it's too boring, is related to the fact that the people were inventing algorithms to classify the images in the ImageNet dataset, which is a huge dataset with I think 1,000 classes, and you can just Google ImageNet and you see kind of all the description. And the idea is that the convolutional neural network, which was used here by these people, were able to reduce the error on image classification by 50%. So it was like such a drastic achievement, so people could not ignore it. And people say, okay, no, there is something in that which we need to take seriously. Yes, in 2017, there was this transform architecture suggested, which is, the pre-architecture for the GPT styles networks and so on. In 2018, the Turing Award, it's a kind of Nobel Prize in the computer science, were awarded to the Benjo, Hinton, and LeCun, exactly for the achievements in the machine learning. And yes, and things will be definitely continued, and we're going to hear more and interesting news about the neural networks. Okay, so and what have happened, in 2012, which allows to all of that to happen, this breakthrough? First of all, we get the ways to calculate it, as we are going to see that if we want to train a train a convolutional neural network, we need the GPUs, and we need a lot of GPUs. And another thing which happens by 2010s, we have already a lot of data in the internet. And that's what the two basic super ingredients which we need. We need the ability to compute things, and we need enough data. Good. And of course, there was some other things like, new optimization algorithms and so on. But, this was two major contributors: a lot of data and ability to to have a lot of compute for the specific targets. Okay. So what is what is a neural network and how it works and how you can train it? Where do we need the GPUs? Why we need the GPUs? Because GPUs will need for efficient performance of this backpropagation algorithm, or it's very efficient algorithm for the training of the neural networks. Okay, so what is a neural network, or what is a simple perceptron model? Mathematically, it could be written like this. So this is a model family for regression, which looks like this. So we have an input vector x. It's going to be multiplied by some weight matrix. So just to give you another vector, afterwards, you apply some function, which is called activation function. And one of the examples of this activation function is a sigmoid function, as we've seen. And afterwards, it could be also multiplied by some extra vector beta, so that it all together, it will give you a number as an answer, not the vector, but the number as an answer. Okay? And that is, this is the most simple feed-forward neural network, or this you can think of this is a perceptron, a very simple perceptron. Okay, so we've seen already sigmoid as an activation function, and we're going to see that, that sigmoid is the choice for the certain class of problem, but, you can have some other activation functions, which for the certain applications might be more efficient. Somebody's saying that they lost the connection. Okay, so Tutukili is saying that it's all good on her side, so. Okay. So feed-forward neural networks, how it looks like, what does it all means? So we have a vector x, which in this image have 3 components. Afterwards, we apply, we have a matrix W, which have 3 columns. Yeah. Or 3. Which we apply to each entry. And afterwards, we apply to each of them, we apply this activation function. And we multiply it by some beta. So each of these could have a coefficient, or it could be just averaging. So to this vector z to produce a number. Okay. So, and what happens when this function g is linear? So if it's not sigmoid, when it's just a linear function, we get normal linear functions. Yes, because if G is linear, what we get beta on W, which is a W is redefined some other vector, or we get some beta tilde. Yes, so we get a linear function. And the most important part about neural networks is really the fact the presence of these nonlinearities, which are coming from the activation function, is what make things so efficient. So using nonlinearity is important because in general, linear regression over the features, of the nonlinear transform data. So that's what make it the combination of these nonlinearities, the sequential combination, because now we have only, so need to go back to here. Yes, this would be called a hidden layer. So we have one hidden layer, but you can have multiples of them, and in each of them we have nonlinearities. And that's when we're making, that's when we're getting something interesting, and we're getting very good data representation. Okay, so but if the G is linear, we're getting back linear functions, and the ability of the model to learn new data is exactly the same ability of linear functions, which we talked already about. Okay. So if we want to use the same perceptron for classification, what can we do? We can do as we've done in the logistic regression in our classification case yesterday. We can take that continuous value X, yes, which we're getting in the end, and feed it into the sigmoid. And if it's above 1/2, it's a class 1. If it's below 1/2, it's a class 0. So essentially, it's absolutely the same, but the difference is we're not summing up just entries in the end. We're also putting sigmoid on top of them, and it's just thresholded. If it's above 1/2, it's a class 1. If it's below 1/2, it's a class 0. That's all. So very simple. Okay, so if we need to do a multi-class classification, it means that here we just need to put that softmax. You remember that yesterday we have it, so that is a bunch of these exponentials. Okay, so, and what we're going to talk about will be related to this modern view on the neural networks, because there is this historical view which considered essentially every architecture as independent, and it requires custom, discussion. But if you will go, I don't know, to the TensorFlow or PyTorch or Torch, which is standard frameworks to implement neural networks, you're going to see that, they don't have a special submodule for CNNs or special submodule for the dense neural networks or special submodules for the transformers and so on. They have just a family of different layers. Or it's kind of like the view on the design of the neural networks. It's just a stack of different layers, which are doing different jobs, but the layers could interact with each other. And, if you put the correct layers together, you will get dense neural network, convolutional neural network, and so on, or mixture of them. So from this point of view, this very simple feed-forward neural networks on the layer language could be rewritten like this. Yeah, so we have our input vector. Afterwards, we have a layer which is doing multiplication by the W, so doing our linear function. Afterward, there is a layer which is doing the nonlinear function, and we're getting answer. Okay, so, and each layer might be parametric function, like here, it depends on the W's. Here, layer doesn't have a parameters, in case if this nonlinear function doesn't have a parameters. And kind of like, that's how you build it. And you can do it, obviously, sequentially. You can form a family of models, so you can have one layer inside, afterwards nonlinear layer, and so on. And typically, typically it's denoted like this, Instead of writing a lot of brackets, it's denoted with the circles, which means in mathematics, this sign means composition. So it means that f of W is applied to X. Afterwards, G is composed with f of W, means that G is applied to f of W. And f of beta, linear function f of beta, is applied to G of f of W of X. Okay, so this is kind of the circles means composition. And that means exactly, this internal bracketing. So, and from this point of view, instead of writing these multiple brackets, we just write a lot of circles. And where this will be just a composition of the multiple layers, but you can think of it's just, you know, function of the function of the function of the function of the function, where you start from the right, you know, kind of this function is applied to the input data, and afterwards next function is applied to result of this function, applied to the input data, and so on. So you get a little cabbage-like or onion-like structure. Okay. So each layer is a parametric function. So it could map vector from with the k component to the vector with the h component. You know, kind of, they could be the same, they could be different, and so on. So it could go down, it could go up. So if we can not only kind of apply layer next to each other, but we can also add them. So we can concatenate them. So they are kind of like, there is two layers which applied in parallel to the same data. So in order to do that, we just need to define, you know, how we add in two kind of the list of numbers. So, and this is just, you know, out of the d and d prime numbered list, we get one list of the length d plus d prime. Okay. So, and that's the two operations which we need. We need to be able to put things kind of in parallel, and we need to put things after each other. Okay. So now we have our view, kind of the layered view. And we can see how we can kind of implement it. Yeah. So we have X. So this is called an input layer. We have our linear function, which kind of, and these numbers W of this matrix are called weights. This is called hidden layer, and everything kind of like X is called input layer, Y is called output layer, and everything in between are hidden layers. So kind of like these intermediate values of input data after you apply weights, or kind of after you apply this, is called units, and kind of like, and you go from one unit to another unit and so on until you reach the output layer. So for example, with the two hidden layers, you'll get something like this. Yes, so you get X, you apply linear function to get a vector of z's. Afterwards, you apply nonlinear function, you get z2s. Afterwards, to this vector, you apply linear function with the matrix W2, you get z3. Again, linear function or nonlinear function, get z4. And afterwards, you apply by the vector to get the desired or trainable output. And that's how this diagram is written in this kind of composition business. And of course, these nonlinear functions or activation functions, these G's are not to be the same, as we're going to see. And in many cases, they are not the same. And the people choose, I mean, kind of the choice of this activation function is also design choice in the neural network training. Okay. Okay, and the same equivalent way of rewriting it with the brackets, but I think this way is much nicer. Okay, so why do we need to care about the neural networks? So because it's, first of all, it enables user to design a new model family that you can capture the symmetries and the structure in the data. You can also kind of, what the neural networks are doing, they are automatically learning features for the certain domains. And we're going to see what does it mean for the convolutional neural networks. Yes, and the negatives are kind of, the cons are, they're very hard to train. Lots of parameters, needs a lot of data. And of course, also we have a lot of design decisions which we need to take. And one more thing which I forget to tell you is why, in the sense, why neural networks were, even on some stage, I decided that they are so kind of important and powerful. There is a mathematical statement exactly related to the perceptron, and it's saying that essentially a perceptron, or let's be more precise. If we have a neural network like this, yeah, and if the kind of with the one hidden layer, and if we are not bounded by the number of internal neurons here, so essentially if we can have any dimension here, we could approximate any function. So there is a mathematical statement which is proving that, if we have a structure like this, and if we have no restriction on the size of the W and beta, we could approximate any function. But of course, the problem is that, when you need to approximate very tricky function, you are getting into the trouble that you need to have a lot of neurons in the hidden layer, and that will lead you to some difficulties of the training. But in principle, there is this statement, and it's called the statement about universal approximation. So, and that is why, in principle, and that's why, many people now is going towards the neural networks by default, because, you have a mathematical guarantees that this model family is covering all spaces of all possible functions. In principle. In practice, it's a different story, but in principle, yes. Okay, so now we need to do several things. Now we need to train it, yeah? So, and how to train it? We know about the gradient descent, but there is a problem that the loss is non-convex, and non-convex, what does it mean? We'll see just now. Yes, and we need to know, we need to have an efficient way of computing gradients. So, because you remember yesterday when we were talking about gradient descent, what do when we were optimizing the parameters of our linear model? So we were choosing some random values of beta, and afterwards going into the direction opposite to the gradient of our loss function. Yeah, and we're doing it iteratively and so on. And but now, if we have a large enough neural network, we'll have a lot of parameters with respect to which we need to calculate gradients. And we need to be able to do it in a very efficient way. And that's where the real magic of this backpropagation algorithm is happening. And without that backpropagation algorithm, and without a little bit of magic of the calculus, which is called the differentiation of the complex function rules, it will be impossible. But because the algorithm is found, and we know that information from calculus, you can perform an extremely efficient backpropagation, or we can perform extremely efficient optimization. Okay, so 2 words again. What is the gradient? Mm-hmm.
There are 2 questions on Slack.
Please tell the name of mathematical proof on neural networks again. I think it's called the universal approximation theorem. Neural networks, or universal approximator theorem. Yes, universal approximation. If you just type in Google neural networks universal approximation theorem proof, you'll see it immediately. Yes, and there is a Wikipedia article about that. Yeah, I think it's, yeah. I think it's, yes. Start checking from that. Let me just okay, so what is the threshold for the data needed in the okay, let me see. You mean here needs a lot of data? That's a tricky question. It depends. But usually you need data in thousands. But there are some thumb rules of how to find how much data you need to have. But data is not everything. But we are going now to in the afternoon we are going to see the example of the MNIThe data set, and this is the data set of the handwritten digits. And over there it will be a data set which have 60,000 entries. 6,000 entries per handwritten digit. So 6,000 ways to write digit 0, 6,000 ways to write digit 1. And that's already enough to train a little convolutional neural network or little dense neural network and so on, so that it works fine. But if you have 100 points, neural networks won't help you, because you will definitely overfit, and you need to look into the methods of the non-neural network type. And also keep in mind that the different neural networks, different architectures, which were different by the number of parameters, requires a different amount of data. But this you see only by training it and see that you're not overfitting. Okay, so let's go to the gradient descent. So we need to calculate a gradient descent. So we need to calculate kind of what do we need to do in order to calculate the optimal weights for solving of our problem and minimization of some loss function. We need to find what is kind of optimal weight. So we need to initialize this weight matrices W. Yes, kind of these matrices, and this beta, you can also think it as the W matrix, but with the dimension 1 by whatever dimension. Yeah, and how to initialize is also a hyperparameter, or it's a parameter with which you need to play. And I will say a few words later about that. And we need to do it for the all layers. And until convergence, we need to do in principle the following. Yes, so we need to calculate the gradient with respect to every layer of the whole neural network of our loss function. And afterwards, yes, calculate the corresponding updated value of the weights for this particular layer. And we need to do it for the whole layers. And already from here, you could see that, if you have quite a few layers, that could be quite a challenging task. Okay, but let's first see how this could be done in a relatively efficient way. At least, this calculation of these derivatives, this backpropagation is dealing with efficient way of calculating of these derivatives, multidimensional derivatives or gradients. So what is the input? So we have a labeled pair XY. We have a model which have, here M layers. We have a loss function for predicted label Y and the true label Y. So we have Y, and this is what's coming out of this model. So we need to do this, we need to calculate this, and we have derivative. In principle, we know how to calculate derivative of any layer. Yeah. Why we know how to do it? Because, derivatives with respect to each entry of the matrix, we just need to take a derivative of linear function. And this is very simple. Yeah. Because what is the derivative of linear function? With respect to the parameter, if you have a function y is equal to alpha x, derivative by alpha is just x. So we know exactly how to calculate it. And we know also how to calculate the derivative with respect to the whatever z. And this we know very efficiently because, again, when it's a linear functions, it's just, these coefficients of matrices. And when it's our sigmoid, we also know how to calculate the derivative of the sigmoid analytically or any other activation function. Okay, so in output, we need to calculate the gradient. So how to do it? So if we need to calculate a multidimensional derivative, so we have a function with the parameters RD, input vector ZK, so that this is a vector in RH. So, and we have two parameters, W and Z, and we need the derivative of FV at W with respect to Z is a matrix. Yeah. So how to calculate this matrix? So this is a matrix of this size, and this is a matrix of this size. So first of all, mathematically speaking, so f of V plus W and Z plus DZ, we can expand to the first order like this. And what one can think, so we can, yes, we can calculate it like this, and we can extract this information. Okay, so we need to calculate a gradient of MSE loss for regression. So we need to calculate the derivative with respect to the W of expression like this. Yeah. So that will be the sum of what? We need to apply this derivative to every entry. Yes. So it will be 2 on this, on the derivative of this. And this is just a constant. So it will be the derivative of this gradient will be applied to this function. Okay. So this will be gradient with respect to the W, and in the same way, gradient with respect to the beta. Because you see the expressions are identical, but just here is a derivative with respect to the W and derivative with respect to the beta. Okay. Now, if we go, and that's where the little bit of calculus is coming in and coming in very handy. Why do we need derivatives for the function? I thought neural networks were optimizing the loss function to obtain the weights. How they can optimize the loss function to obtain the weights? No, but I mean, what you are doing, you are doing a gradient descent in the space of the weights, such that the loss function is minimized. Because how you can optimize the loss function? Loss function is a function, you cannot optimize it. So, I'm not sure that I fully understand your question, but the loss function is just a function. No, but I mean minimize. Okay, so, but I mean, like, how do you minimize the loss function? Because if you don't change, how do you find the weights? Because what the neural networks are doing, they find in the weights which are minimizing the loss function. But in order to do that, what do you need to do? You need to change the weights. Yeah. And in order to change the weights, so we need to change the weights such that the loss function is minimized. And for that, we need to have a derivative of the loss function, because we need to do it. It's really like a gradient descent for the linear model, but now it's for the weights of the neural network. Okay. Let's now see how to calculate. I hope I answered. Agreed. You also have a derivative of the loss function and the loss function and the yes, but why do we need to have a derivative of the loss function? Because when we're changing the weights of the neural network, we need to know how we change it so that it's minimizing this given function. Because you need to think that what the loss function is doing, it's giving you energy landscape. And I think somewhere down the slides, there will be a slide with the typical and very poorly optimizable energy landscape of the, or kind of the loss landscape of the neural networks. And now you kind of like, you are, as a function of this weights W, you are somewhere on that landscape, but you want to find the W such that you are in the, ideally in the global minima of that loss landscape. And how you can do it? The thing, when you're choosing the direction, you need to use, we were talking about the gradient descent. So you need to choose a direction on which you can go down the hills. And for that, we need to calculate, and where the hills are coming from, the hills are coming from the loss landscape. So we have to take a derivative of the loss function. Because here we're taking, because what we're doing here, we're taking here a derivative of the neural network. But we will need to take a derivative of the neural network. Why? Because when you take a derivative of the loss function, it's have a neural network inside. You see, kind of like, because we need to calculate this to update the weights. Yes, where is the formula? Yes. So that's how this is just a standard gradient descent. Yes. So we have our parameter. In order to update parameter, we need to calculate the gradient. And gradient of what? Gradient of the loss function. But the loss function have a functionally inside our neural network. In principle, you can say that, okay, you need to evaluate it and to do it multiple times. But by doing this analytical game, which I'm showing you now, you can do it much more efficient. Because you can say that, okay, no. We're going here to calculate function, and afterwards we're going to numerically calculate somehow derivative. But that's going to be a very inefficient process. It's much more efficiently to do a little bit of legwork now with analytical expression. And what essentially will be coming out of that you can rewrite all this process on the language of the matrix multiplications. And that's why the training of the neural networks are so efficient, because the matrix multiplications is the one of operations which our GPUs are very good at. And the TPUs are even better. Okay. So I hope I answered. So we need to take a derivative of the loss function, and derivative of the loss function is related to the derivative of the neural networks. That's why we need to learn how to take the derivatives of the neural networks in the efficient way. Okay. So, and here we really need to do the composition rule. Yes, so kind of derivative by the betas of this guy will be just a derivative, because this is beta is standing here, will be just a derivative of the function beta with respect to the everything which is sitting here. You can write it as a z. And because this is a linear function, you can relatively straightforward write what it's going to be. Okay. So with derivative with respect to the w, the situation is a little bit tricky, because w is standing behind, three steps of the composition function. But what is helping us exactly the rule of calculus, how to calculate the derivative of the composite function. Yes. So what would be the derivative with respect to the w of this function? That would be the derivative of the first function with respect to the argument here. And as I mentioned to you, we know how to calculate it, because this is a derivative of the linear function. Now, the derivative of what is remaining. Yeah. What is remaining is derivative of our activation function, which we can pre-compute in advance. Yes, because we know the family of activation functions is not that large. And I just told you only about the sigmoid. And you can show that the derivative of the sigmoid function is reducing back to the sigmoid, essentially, with some constant coefficient. Okay. And afterwards, derivative of, again, of the w itself. And you see now what are you getting? And it's very interesting, because from now you can already see that there is a structure, because we've seen that this guy will be some sort of a vector or a matrix. This will be a vector or a matrix, and this will be a vector or a matrix. And you can interpret this derivative exactly in the way of matrix multiplication. So what do we have in general? In general, we get exactly this sort of compositions. So when we have a neural network with the m layers, yeah. So when we need to calculate a derivative, if we denote zg is a kind of intermediate result, when we apply only g layers. So when the g is 0, so it means that we are here, it's x. And when the g is anything else, it's just will be the application of the g's layer to the previous result. So, and what is the, in general, derivative of our neural network to some intermediate layer? So it's a derivative with respect to the zm minus 1. So what is a derivative with respect to the zm minus 1? It's a derivative over what is standing here with respect to this function, and now derivative multiplied by the derivative with respect to, with respect to exactly these parameters. So, and that we know again how to do, because this is linear function. So fw of m is just a linear function, or function where we know the derivative if it's an activation level. So essentially, you can write it immediately, for any for any order. You can write it very straightforwardly. And in the moment when you add here the matrix multiplication interpretation of these operations, suddenly you see that, in order to calculate these gradients, you just need to pre-calculate certain class of the matrix multiplication operations, which are, as I mentioned, are relatively straightforwardly implementable by the GPUs. Okay, so for arbitrary layer J, you just need to go until you reach the J's level. Yes, so kind of you take derivative of the levels which are before the J on the J plus 1 level, so one level before. You still have a derivative with respect to the internal argument, and the last one will be the derivative with respect to the already this matrix of parameters. Okay, so this is a very simple idea. So this is a combination of two things: the composition rule and kind of, and that's what kind of, and essentially that's all. And the fact that we know exactly, sorry, and the fact that here we know exactly which functions are we dealing with. So, and we're dealing with only with the linear functions plus very narrow class of activation functions for which we know exactly how these derivatives are looking like. Okay. So if we introduce extra nomenclature, so the portion shared across the terms is dj. So if this is all the products of the derivative with respect to the internal argument up to the our layer. So we get that the derivative on every kind of on every layer j is kind of derivative with the external or internal argument up to the derivative over the matrix. And this also kind of this way, you can see that you can formulate it in a recursive fashion so that you can calculate it automatically in a recursive way. So if we want to calculate it for the j+1 level, we'll have here j's level, which we're just calculating, and so on. And kind of like this could be seen in the following diagram. So, and what is the kind of the process of the training of the typical neural network is looking like? So you have your input data. For the sum values of the w's and betas, you do forward pass, so you calculate y hat, yeah? And afterwards, you calculate a backwards path. What the backwards path means is that you need to calculate all of these derivatives, and you can calculate this derivative, and afterwards, in order to calculate this derivative with respect to these parameters, you will need to, or with respect to these parameters, you will need to derivatives here, which you already have. To calculate the derivatives here, you will need to derivatives here, which you already have, and so on, so that you can use that information to calculate all the derivatives efficiently. So, and kind of like we have this W, so as we're moving through, we're calculating through the each layers, each value. And afterwards, when we're doing the backwards path, we have here this D5 on our language, yes, with us DJ. So we're recording the derivative with respect to the beta, or we can affect the W's here. As we keep going, and we keep going to calculate D4, we need a D5, yeah? So we come in here, we can have a derivatives here, so we can update the layers here. And as we go, we will have a derivative here, but these derivatives will be just recursively calculated from all the previous derivatives which we have. And we completed the backwards path, and we updated the W's, okay? So forward pass is we're computing the values in all the layers. Backwards path, we're calculating all the derivatives. And the final output, we know now the gradient for the each j. Okay, so now we get our gradient descent, and now we can apply this rule. And now, moreover, we know a GPU efficient way of calculating these things. Okay, so and we can compute the gradients and we can update the parameters. Okay, so, and this is a very, very basic idea of what the neural network is and how the neural networks are trained. But there are, kind of like, if you just want to go this way, it would take you kind of like, it might take you quite a long time, and you might need to do some, special kind of try to use a special tricks to do your process of training that. And so there is some standard list of things which you need to do. So, and let's talk about them. So first, optimization. So, and this is one of the famous pictures from one of the academic papers about the neural networks. So first of all, we're dealing with what is called non-convex optimization. So this is a loss landscape in a very simple case. And you could see that, you want to fall into this minima. But if you get stuck somewhere there, or somewhere, okay, maybe here you're not stuck, but you can also stuck here, you're going to have quite a bit of a problems, yes, because if you're stuck in a local minimum or saddle point, you can really stuck there. As there is also a problem of exploding or vanishing gradients. So where that is coming from, because you've seen in our procedure when we were calculating these derivatives, we are multiplying matrices, or we're just multiplying a lot of numbers. And you have two scenarios, what is related to this exploding and vanishing gradients. So if you multiply too many small numbers, you will get a very, very small number. So when you're calculating your gradients will be very small. Or when you calculate, or when you multiply larger numbers, and many of them, you can get a very huge number. And so your gradient could become super huge. So, and this is always not good, because you want everything to be kind of nicely comparable to each other. So that's a problem which needs to be addressed. And yes, there is also a problem of ill conditionings, but there are some heuristics or thumb rules or so on, whatever you want to call it, which might work or might not work. And if they're working, you might want to try them. And if not, you might want to Google or go to the Stack Exchange and see, or Stack Overflow, and see, have other people seen the problem which you are seeing. And the most of the problems which you are going to have with the training of the neural networks, somebody already had. So yes, Google it. So what to do with our gradient descent? So we can initialize, and we need to update the parameters. Yeah. So the first thing which we can try to address is this bit. So, and how we want to address it. And there are various strategies to address it. So kind of like, because here we need to sum over the all entrances, over the all indices. And sometimes it might be very difficult. And we might try to play kind of with calculation of that sum. So one can try to do what is called, instead of doing a gradient descent, one can do a stochastic gradient descent. So you can just choose some random directions. Or what you can do what is called a stochastic mini batch gradient descent, meaning that what you are propagating for directions, so kind of you're not doing it for the all entries of your input data, but for this random subset. And you can have a multiple subsets, and you choose it accordingly. And kind of if you walk long enough in the energy landscape, in that case, you have a good chance that you will get out kind of your local minimum. Because if you calculate the gradient not to respect to the all possible directions in our language, where is our landscape? It means that kind of like, if you're starting somewhere here, just by luck or chance, you can get even if the better direction will lead you to this local minima, just because you're calculating gradient not to respect to the all axis, you can go in this direction. And if you do it several times, you could find the better solution. At least that's what the practice have shown. So kind of this mini batch stochastic gradient descent, it really works. Yeah. So another trick is that you might need to play with with this learning rate, or kind of play with how you apply this gradient descent. So because here it looks like what you are doing like you're moving with a constant velocity, but now you can move like with the acceleration. So you can move, you might kind of pretend that now you're moving with some sort of acceleration. And that's also have shown that it works in some scenarios. And this is kind of what we're discussing here. It's the different types of optimizers. And again, all of these optimizers are implemented already in, not in scikit-learn, but in the neural network packages like a TensorFlow or PyTorch. And we're going today to play with a TensorFlow. Okay. So it's something like you're moving with a not constant velocity, and that is also could be useful. Okay, the intuition that you see, that kind of this intermediate parameters, it's intermediate parameter rho, it's hold the previous value of updates, and it's kind of, it works like like an acceleration. And you have, but as a price for that, you get an extra hyperparameter which you need to play with. But again, for the most cases, again, people have figured out if it's makes its way into the packages like TensorFlow and PyTorch, it means that the people have already trained enough neural networks using these optimization routines, and there is some generic recommendations. For example, for this hyperparameter, you see the suggestion is 0.9 or 0.99. Okay, so there is another type of gradient descent, which is called Nestor of momentum. And that's, again, the idea is, again, is very similar. It's some sort of that you don't move with a constant velocity, but you move with some sort of acceleration. For us, it's just, again, from the practical standpoint, that you need to know that, the default optimizers for the gradient-like descent are listed kind of in the compiler, are not necessarily that one which you need to use. You can try it, but if it doesn't work, you need to know that, you can apply different versions of the gradient descent. Okay, and there is some, some intuition behind this, what is called this Nestor of momentum, so that, the gradient is pushing to you in one direction, momentum is slightly different, and so you are walking in the slightly off the gradient direction, which helps you to avoid overshooting. And if you walk enough, you get to the optimal. Yes, another thing is that the people play with the adaptive learning rates, and you see there is that if you look what the optimizer is, you will definitely see the Adagrad and RMS prop, and what they use for the learning rate, they use slightly different rules. Yeah, kind of like they use the updated different rules by this rule or kind of by this rule. Okay, so you just need to know that this is your degree of freedom in the training neural network, and that's what it is. Yeah, so kind of Adam is similar to ARM prop, but use the second moments of the gradient. And I think we're going to use Adam because Adam is now by default, and it's used very, very nice, and it works very nicely. But again, if Adam optimizer doesn't work, you can use some other optimizers, or you can use the vanilla gradient descent. And the Adam is this RMS problem with momentum. Yes, and see, it's even said that it's mostly commonly used optimizer, which is true, which works in the most cases. Okay. So learning rate, you see, it's quite an important hyperparameter, and you can, by looking on the loss behavior, you can understand what's happening to your learning rate. So, and this is the example of realistic learning rate for the multiple epochs, which we're not going to train for so many, but even this is 100 epochs is not that much. The large neural networks which are used for the computer vision on natural language processing trained for hundreds or tens of thousands epochs. Okay, so what do we have here? So if your learning rate, kind of like if your loss on the training data is behaving like this, it means that you have a very high learning rate. So if it's kind of converges, but the converges, not to the zero, it means that you still have a high learning rate. And the good learning rate, you see, it's roughly more or less like a nicely exponentially decreasing. So if it's decreasing exponentially, but quite slow with the number of epochs, probably your learning rate is a little bit too low and you need to increase it. But you need to see so that, that your nice exponential or it's not necessarily exponential, but exponential like decay is not begin to go high. So it's essentially, it's an extra parameter which you can play with. And there are tactics how to play with the learning rate. Okay, so this is the example of the learning rate with the training error from the deep learning book. And you see it's look very nicely exponentially decreasing. Okay, so, and there are some other strategies of dealing with the learning rate. So you can, if you can change your learning rate every time when the validation loss stagnates. So kind of when the validation loss is becoming kind of like constant, you can decrease the learning rate. And you can see that if it works or not. So there are different strategies what you can do with learning rates. Okay. So essentially, what is the key bit of knowledge from this optimization step is that you can have a different optimizer, default choice, which works good enough with the Adam optimizer, but it's not limited to it. And you need to play with learning rate. Okay. So in advanced case, you might use some shadows for the learning rate, or in normal cases, you can just take a range of the learning rates and see how the loss is behaving as the number of runs of your neural network. Okay, so now we're going to talk a little bit about activation functions. So the only activation function which I told you on nonlinearity, yes, that G function, was a sigmoid. Another function which is used, which looks very much like a sigmoid, is a tanh function or hyperbolic tangent. And it's also used quite frequent and quite often, but that is kind of, this is two historical activation functions. And as usually what people see that, practice have shown that this very often is not the best choice. And it's not the best choice because of, yes, of this vanishing gradient problem, or kind of like when you need to multiply the derivatives of the sigmoid function, and you see the gradient or derivative of the sigmoid is looking like this. And if you are somewhere, kind of like, first of all, if your x's are a little bit here, you get zeros. Yes, and kind of you can get quickly multiplied to zero. And the tanh will look in a similar way. And currently people figure out that the very nice activation functions are looking much easier. And one of them is a ReLU, which looks very simple. For negative x is 0, and for positive x, it's a linear function. But because it's distinguished between the positive and negative x's, it's already a non-linear function, which of course could be written as maximal of 0 and z. Derivative looks very simple, and it's much faster to implement. And of course, one just needs to be a little bit careful around 0, because you have here kind of like the jump. But again, which function you need to check? You just need to see how the training is happening. And this is one of the examples. Yes, so we have a training error as a function of number of epochs, and you have a tanh as an activation function or ReLU. And what you see essentially, they both converge, but ReLU converges much faster. So, and this gives you a very simple, this is extra parameter which you can play, but the recommendation is that for in kind of internal layers, people put usually ReLU or some modification of the ReLU, because, ReLU is looking like this. So for the negative, it's 0, but sometimes now people would begin to add that for the negative, it's just some other linear function, usually much smaller than, because here just f of y is equal to y, and here is, f of y is equal to some negative value of y, which is kind of like smaller. Okay. But generally, ReLU is a good standard choice. And, people come up with the new activation functions, and you're welcome also to play with that. But again, we're going to use ReLU in the example in the afternoon. Okay. So next tips and tricks are related to the managing of the weights. And the weights, kind of like, I told you how to update the weights, but where to start the weights is also a very good question. And naive thing which people can suggest to start from 0 is a very bad choice, because we need to multiply matrices, yes? And when we need to multiply matrices, we need to multiply, and there will be too many zeros. And also, if you start equal, all the gradients are equal, which is also not good. So, and there are some, again, people trying to play games in initialization, and there are a couple of strategies. So you can start with the, what is called this uniform distributed random numbers, or you can start with the Gaussian distributed random numbers. And here, even people kind of experimentally came up with the thumb rule, which is saying that, so you need to start with a Gaussian number with a 0 mean and the deviation 2 divided by the dimension of the input, or for ReLU activations and for the tanh activations, Gaussian random numbers with a standard deviation 1 over the dimension of input plus dimension of output. Okay, so kind of like, this is relatively straightforward, but again, this is a hyperparameter which you can play with, and this is what you can just set up in your discrete, kind of in your PyTorch or TensorFlow. Okay, so there is one more problem which kind of people see very often, and that is adding the extra layer, which is called batch normalization. So because during these update rules of the layers, what happens is that, this, as you see, kind of like we're starting from the distribution of the values in the matrices as kind of Gaussian numbers, but that might kind of like change as it goes, and sometimes it's not good. And what is happening? You just renormalize your layers, the values of in your layers to be again to do a covariance shift so that it's again normally distributed. Okay, so and there are some kind of observations that adding this batch normalization makes the training process much more efficient on the corresponding validation accuracy. And what I would recommend you to give a look at number of training step axis, and the M is standing for million. So now you know why you cannot train a world-class convolutional neural network which can recognize which can compete on international level in your basement, because you need to do a few millions of epochs, and in order to do that you need quite a lot of compute power. Okay, but essentially what again is for us, we just need to add this layer into our network. Okay, and there are also some we can do regularizations, and we already seen with you what is the L1 and L2 regularizations, but now we can do it for the layers. Okay, and we can do this one, or there is also what is called Frobenius regularization. Okay, so now is a less obvious thing which you can do, because these things were clear, but this is a very interesting thing which have a very nice intuitive interpretation, which is called dropout. And this is related to the fact that in the training, what you want to do from time to time, you want really randomly drop out completely to put the weights, certain weights, to 0. And why you wanted to do it? Because you don't want that in your training process that your neural network learn some path through the through the weight matrices, where you get a certain values there being large, and so that it will be a dominant part of learning some knowledge. And in that case, it might learn one of the side of knowledge, so to say, if you can interpret it in this way. And by zeroing out randomly the weights in the neural network, you force the training algorithm to learn in a generalizable way, to learn overall, so to say. And it's again, for us, it's a standard thing. We just add the layer, which is called dropout layer, and we supply the probability. And for the computer vision problems, for the neural networks which are learning the visual information, the typical dropouts are going above the 50%. So exactly to make sure that there is an averaged out information learned. Okay, so for example, yes, you do the input layer, you have a fully connected hidden layer, and afterwards you have a dropout layer where with probability 50%, you will zero out the entries, so that whatever information is trained here is have to train in such a way so that the same information is encoded not only one hidden neuron, but it's encoded over the whole neurons. I think it's a very counterintuitive. I mean, after it's explained, it's very clear that, oh yes, of course you need to do it, but it's a little bit counterintuitive if one would tell it to you, oh, would it be a good idea to zero out some values in the hidden layer? And the answer is it could be if that's what you want to achieve. Okay. So intuition, it's a form of regularization. It's encouraging robustness to the missing information. Each neuron works in many different kinds of inputs, and so on and so forth. And you see, and there is some hidden connection to ensembles in this sense, so that each training iteration is a training slightly different network. So you get, some sort of average out effect as an ensembles. Okay. So dropout test time and test type, so we can stop dropping out neurons. So we can just apply, dropout, and we can see, does it work or not, and we can play with the dropout, and sometimes it works, sometimes it don't. Okay, so And the last bit is related here to the managing of the training. And one of the things which one want to implement is called early stopping. And the early stopping strategy, one can see it from this image. And what do we see here? So we see here the training loss on the training loss and validation loss. And training loss, as you see, kind of like we train here over the 200 epochs, so over 200 iterations. And we see that the training loss is going down. And afterwards, it's not really changing anything. And essentially, validation losses begin slowly to increase. But what that is telling us, if you remember, bias variance trade-offs from yesterday, so that essentially we need to stop somewhere here. So an early stopping is a standard function within the both PyTorch and TensorFlow. Then you can say that, okay, for the certain thresholds, so for the certain value of the differences between the training loss, you just stop and don't train anymore. Because in that case, essentially we haven't learned anything new after the epoch 50. And one more step which could be done is called data augmentation. And this related to the very simple idea. So that, if we have, for example, the image of the cat, and obviously, this is the same image of this cat, and this is the same image of this cat, and this is a still cat, the same cat, yes? And why you wanted to do that? So when you don't have enough data, so data augmentation could be a very good idea, because, and what you do essentially, what is the difference between this image and all of this extra? So this is this image which is rotated by a little angle, this image reflected in the mirror, yes, and kind of like a little bit scaled up, again reflected in the mirror and twisted, and a little bit scaled up. But so as a result, what are we getting? Instead of one image, we're getting 7 images, yeah? So, and for us, as a humans, it's clear that it's image of the one and the same cat, and we are not learning anything new. But the algorithm, because for the algorithm, what will be the image of the cat? The image of the cat will be just an array of numbers, or 3-dimensional array of numbers. So because it's a 3 colors, RGB, yes, so it will be in each channel, you have an array of the size of this image. So, and the computer doesn't know that this is a cat, and it doesn't have an image of the cat. So for computer, this image and this array are 2 different arrays, and this it will be just, the way how you can increase the amount of data which you have. And the interesting point here is what people are doing now. They're now designing such neural networks, and this is called geometric machine learning, which take into account these things automatically. Because what you can design the layers which will be invariant with respect to the, for example, rotation, or with respect to the reflection of your input data. And in that case, what is observed that, kind of like, first of all, you get much less parameters in your neural networks, and what you get, kind of like much better training, or if you get, the same precision, the time which take to train these neural networks is much shorter, and the neural networks are smaller by themselves. So kind of like you can play this data augmentation game, or one can also kind of like, currently, I think that there are already packages which are dealing with that, what is called this geometric machine learning approaches, or geometric neural networks, which can incorporate certain symmetries, because mathematically speaking, rotation or reflection is a symmetry. So kind of which can incorporate these symmetries automatically. Okay. So now we're going to talk, because now we finished essentially with the neural networks as a dense neural network, and now we're going to talk a little bit about subset of this neural networks, which are called convolutional neural networks. And in order to talk about that, what we need to talk a little bit about, what are the images, and why in general we will need this kind of an extra bit. And why we need an extra bit, sorry, oh, okay, I don't have an image of our dense neural network for now, that we have it on some previous slides. But the thing is that, if we have a fully connected neural network, and we have enough, kind of large enough number of hidden layers and large enough number of neurons, we're going to see that we're going to have a huge number of parameters, which could be easily several millions of parameters with not such a large kind of a network, kind of like 3-4 hidden layers with the 50 neurons each. And we will see that suddenly the number of parameters is exploding. And it means that it will be very difficult to train such a neural network. And now one would think, what can one do in order to play the game of the neural networks, but be able to reduce the some efficient strategies to reducing the number of parameters. But as a result, of course, in convolutional neural networks, you will still have a huge number of parameters, but the neural networks will have a much larger capacity for the solving of the certain classes of problems. And these classes of problems related to the symmetries of the image information, or any information which have what one can say the locality property. So, or the properties so that what is important is not what this point is, but this point and some neighborhood of it. Okay, so, but before we're going to speak about that, let's see how we can represent the image. So what is the image from the computer point of view? From the computer point of view, image, if it's a black and white image, it's just a matrix, yeah? So because each image is a bunch of pixels, and each pixel, if it's a black and white, is a number from 0 to 255. Yeah, kind of like which incorporate our grayscale. If it's a colored image, it's a 3 arrays like that, yeah? So it's a 3 squared arrays, which each array corresponds to each channel, red, green, and blue. Okay? And each of them, the standard notion is a channel. Okay? So what do we have typically in the images? Images are, have certain degree of the translation invariant. So it means that if we have an image like this, we can move it a little bit, the image around, and the image still have the same information. But of course, if we move by 10%, 20, 30, or even 40%, it's still the same label, but maybe afterwards, we can do some shifts with the images, and of course, maybe not the full rotations of the images, but we can do it, and the information is still there. So we need to explore that property. And there is another property which is called translation equivariance, which is if we consider the problem of the object detection, yes, if we translate the image, so if we shift the image, the object is translated similarly to the shifting of the image. And now, what are the crucial differences between the what new are these structures are going to introduce? And essentially, what new will be 2 new type of layers. One is called convolutional layer, which is essentially capture equivariance, and another is a pooling layer, which is capture invariance. But it just for us is what we need. What if we work with the visual information, or as I mentioned to you, information which have certain locality properties, we need to define 2 new type of layers. One is called convolution, and what the convolution do, it's take your image, your input image, and it's apply a certain mathematical operation to a subset of image and project it on the single value here. And afterwards, it will going to be shifted and projected onto this point and so on. And how it's shifted is a hyperparameter, and the fact that it's applied, here with a little bit of space is also a hyperparameter, and that will be a convolution layer. And weights of this convolution layer, of this convolution layer, weights of what is a mathematical operation is applied, will be exactly the thing which is going to be trained. And here, instead of training, so you get that this blue layer is related now to this green layer, but now instead of having that, each blue cell is related to every green cell and vice versa, and you have a huge number of parameters, yes, because this one is related to how many we have here, how many greens we have. We have 25 here greens, yes. So we have 25 by 25. Instead of having 625 parameters, it will be only the 9 parameters of the small 3 by 3 cell. And one would think that, don't we go into lose information or not, kind of like is it justified or not? But the practice showing that doing operations like this with images works very well, and that's exactly how ImageNet managed to beat any other previously existing structures. And what the pooling layer doing, it's doing some sort of averaging out. And one of the typical things is what the pooling is doing, it just taking the cell, for example, 2 by 2, and you can specify the size of the pooling and replace it by the, for example, maximum value, or it could be replacing it by average value of these 4 cells. So you're going from the layer 4 by 4 to the layer 2 by 2, where essentially every entry is just replaced by, in this case, by it's called the max pool layer, by the maximum value. Okay, so what are these convolutional filters, or what are these things, how they work? So convolutional filters are working like this. So for example, if we have a filter like this, so what does it mean? You can think about that this is black and white matrix with the entries, from 0 to 255. Yes, kind of like, because this is a grayscale, which have a certain values. And essentially what you do when you apply it to this, to this part of the image, you just calculate, the product of the value here on the value on the image, on the corresponding value on the filter, and you sum it up, and you go through the whole image. And so the result of application of this filter to this image is looking like this. And one might think that, okay, that looks horrible and useless, but as we're going to see that, this is just an example of the filter, and it might be useful for some structure or for some problems. Okay, so 2D convolutional filters. So we have a 2D input X, and we have what is called kernel, and we just calculate the following action. But again, we don't need to kind of try to understand it, because what we just need to know that the inputs into this filter will be the training parameter of the algorithm of the neural network. Okay, so and here is some example of the classically known filters. So if we have a filter like this, -1, -1, -1, 2, 2, 2, -1, -1, it's going to separate horizontal line. This one is going to do the vertical lines. This is 45-degree lines and the 135-degree lines. And this is examples of the edge detection kernels of filters. And if we apply the convolution with the horizontal kernel, you see what we're getting? We're getting that, all the vertical lines, they are different from all the rest. Okay? And the beauty of the convolutional neural networks that, kind of like before neural networks, people were spending a lot of time to invent these filters. And you see kind of like this is the edge detection filters or edge detection kernels. So kind of somebody came up with that, so that if we wanted to detect the edges, what do we need to do with an image? So, and they invent these filters. But now, yes, I mean, this design of the filters is left to the training algorithm, and it's happening in automatic way. And that is the beauty of convolutional neural networks and the process of this training. Okay, so historically until late 80s, kernel parameters were handcrafted, yes. And there are whole books on the kernel methods, and they are dealing with this, how to detect, how to invent these kernels which are going to do for you certain action. For example, in the pre-convolutional neural networks time, there was a problem. We have an image of the human face. Can we create an algorithm which could recognize a human face? And people were designing the kernels which recognize the eyes, nose, lips, and so on. And if you have all the components, that is the face. And so kind of like it was very inefficient. And now the parameters of these filters are now trained automatically as a part of neural network, because they are exactly those weights which are now trained. And essentially what you get, you just, because now you just do this kind of random number, or kind of, you just add convolutional filters to your convolutional layers to your neural network, and using the backpropagation, they're trained. Okay, so for example, yes, so kind of like you have a layer. So now there is a example of application of this layer. So, and if it's a filter with a parameter 0, 1, 2, 2, 2, 0, 0, 1, 2. So when it's applied to this matrix, it will produce, you know, metrics like that with a number. But now this number 0, 2, 0, 1, 2, 1, 2, 0, 2 is a learnable parameter. So, and these numbers will become those numbers which are the best for your machine learning algorithm. Okay, so convolutional layers have two parameters. One is called stride, and another is called padding. Okay, but that's probably on the next page. The stride is, you know, how much we wanted to because, you know, we can apply this filter of 2 by 2 to these four guys, and afterwards we can jump to the next four guys or next 2 by 2, or we can still involve this kind of the last column of this square, so 0, 1, 0, 0. And this is called stride. You know, stride 1, it's mean no skipping. So it's mean that we're applying here, and afterwards we're just moving just by one column. Stride 2 will be moving by 2 columns, and so it means that it will be like independent squares, and you can play with that and see how it works. And these zeros around is what is called padding, as I think it's going to be on the next page. Yes, padding. It's adding the zeros at the edge. So when you apply the filter, so that you kind of apply the filter, kind of, you are not losing this kind of the data which is in the corners or in the boundaries. So you can just apply the filter, and you can, and padding is called adding zeros to the edges. And you can decide, you know, how much zeros, how many rows of zeros you need to apply as a function of the size of the kernel. So, and again, this is the hyperparameter choice. So this is a choice which you need to do and see how does it work. For example, here you have on this example, stride of 2 and 0 padding of 1. So kind of like 0 padding of 1 means that you have a 1 line of zeros, and stride of 2, it means that you see, first you apply the filter, kind of the red square, and afterwards it's not going to the kind of moving by the one column. It's becoming the violet one by moving like over 2 columns, and afterwards moving again, but 2 columns is becoming the green one. So, and that's why we get here, out of this 5 by 5 image, we get a 3 by 3 image. But if we have a stride of 1, yeah, we'll have a 1, 2, 3, 4, 5. Yes, we'll get again 5 by 5 image. Yeah. Okay. So in convolutional layers, so we have a parameters, which is a kernel size, you know, what is the size of these metrics. And it could be, in principle, it could be different along the X and the Y axis. What is the stride, amount of zero padding, and number of output channels. And in which sense, so that you can have, you know, several filters, which kind of, you can have one input layer and you have several output channels. Okay. So you can think about it like this. So you take a flat image, which is kind of thickness is the number of input channels. Yes, for example, you know, if it's a original image, if it's a black and white, the input will be only one input channel. If it's a, you know, colored image, it will be 3 channels. But again, you know, if it's whatever any other information, so, you know, if it's some astrophysical information, for example, and this is some astrophysical photos of the galaxies, and if they're taken in the several wavelengths, the number of channels will be the number of wavelengths in which images are taken. And you are mapping it using this convolution to the number of filters, and the number of filters is a number of output activation maps. And kind of you do this procedure several times with the several other layers, and you can achieve, you know, a wonderful recognition quality. Or you can. Okay, so and here is a little quick example. So we have a kernel size 3, stride 2, padding 1. Again, kernel size 3 is 3 by 3 matrix. Padding 1, we have 0 around, yeah, only one line of zeros around. And stride 2, which means that we're shifting by 2, and you can sit down and calculate it, and you see that you're supposed to get matrices like this. Okay, so 3 input channels, and the kernel size is 3 by 3 by 3, so it's a little cube. 2 output channels, and you can estimate the total number of parameters. Okay, so now pooling layer. So that is two very different layers which we didn't have in the previous neural network discussion. So what the pooling layer is doing, so we have some input image, and for example, what does it do? It's within a certain range, it just takes a maximum value. So as you move, so take the maximum value and you get like, you know, a coarse-grained image of your input image. And you might think why you wanted to do that. But in fact, you know, that's the way how you can learn the kind of like what is this coarse graining or averaging out is doing, or kind of the maxing out is doing. It's make the most important part of the image to be separated from the least important part of the image. And in fact, it also works very well. Okay. So for the pooling layers, you have several hyperparameters. So you have a kernel size. Again, you need to decide maximum of how many blocks are you taking off. Stride, again, zero padding, and pooling function. It's almost always max, but you can also do averaging. But you know, usually it's a max. Together, these determine the relationship between the input tensor shape and output tensor. Okay. So, and unlike the convolution, pooling layers operates on the channels separately. So, and input channels and output channels. Okay. So, what do we have? We have convolution and pooling layers. So, convolution is translation invariant, meaning that, you know, we can. So, pooling layers are also translation invariant. So, if the object is translated, convolution input is translated by the same amount. So it's produced image shape features. Yes, and kind of, yeah, kind of, and in the modern architectures, essentially that will be the two major changing layers which are happening for our computer vision tasks. So we'll have a convolutional layers and pooling layers, and on top of that we'll have all the rest layers which we have from the standard neural networks. Okay, and I think, as an example, I'll show you the example of this AlexNet, which was used in that famous ImageNet competition. So, and it contains of, you know, let's go here. So your input images were the colored images. Yes, and you know the statement that there is 1,000 softmax, so it means that it was a data set of the images of the colored images of different objects, 227 by 227. Colored images means that's why we have 3 layers, and they belong to the 1,000 different classes. And what was happening? So you get the first input layer. Afterwards, you apply the convolution filter, which was 11 by 11, and it have 96 different filters. And it was applying the pooling, and afterwards 5 by 5 convolution, 256 filters, 3 by 3 convolution, 388 filters, and so on. So you see there is a sequence of convolutions. Some convolutional layers are followed by the pooling. So yes. What does it mean? It's local normalization, pooling, kernel size 3, stride 2, no padding, ReLU activation. Convolution size, kernel 11, stride 4, 96 output channels, no padding. So yes, kind of like it's very reproducible architecture. And this is something which one can probably train on the modern enough GPU of, you know, I don't know, of 4x or 3x NVIDIA family. And it's probably will take you probably a day or less than a day. But kind of other modern architecture, but I mean, this is no longer a modern architecture. I mean, modern architectures you cannot train already. So this kernel or these convolutional layers are coming with the pooling. This is just the convolutional layers. Again, the convolutional layers with the pooling. And afterwards, there was a standard fully connected layers with the 4,000 nodes, and it's finished with a fully connected layer with 1,000 node, which is a softmax because you have 1,000 classes. And yes, kind of like you see that how you increase. So you decrease the dimension of input data. Instead of 227 by 3, you get 55 by 55, but you know, the width is 96 different representation of the same image. Afterwards, it's become 27 by 27. And afterwards, you do another convolution, it's become 256 of 27 by 27. And okay, you apply pooling, you get 13 by 13 of 256. And you see, kind of, you get more and more filters. And in the end, when you get, you know, 6 by 6, but with a two different 256 filters, you fit it into the fully connected layer, another fully connected layer, and there is a soft max already to detecting the results. And kind of one is performing this optimization, and one can get the results. And as I mentioned to you, there is a kind of example of the ImageNet competition. So AlexNet was here, and it's essentially only 8 layers. Afterwards, within a few years, it was still what is called the kind of not too deep neural networks. And the kind of essentially kind of the big jump was by the ResNet, which is, I think, by the Microsoft, which have 152 layers. And modern networks, you know, have this order or larger order of magnitude of the number of layers. And kind of like if these things could be trained, as I mentioned, on the usable GPUs, kind of this side of story is requiring already, you know, access to the GPU clusters. Okay, and I think that would be it, what I have for you. Let me see where we are. Okay, there is not too many questions, or there is just no questions. So I think, yes, I will finish with my lecture here, because, you know, the next what we need to see how to train some of those things, and there will be a couple of tutorial files around that, and that we are going to see after lunch. And yeah, so please ask your questions.
Thank you, Prof. There is a question from Zepo on Slack.
After yesterday and today, can we say that the significant difference between machine learning and neural networks is in that neural networks are good at handling nonlinear function, where the machine learning are better handles more linear functions? Okay, no, I wouldn't really, you know, I don't want to make this, you know, kind of like putting things to the buckets. You know, neural networks is a part of machine learning. Yes, neural networks are good with the handling of nonlinear data, but you might think about the neural networks, you know, as kernel methods, you know, as a kind of very, you know, classical 80s style kernel methods, but on the steroids, you know, kind of like, I wouldn't like to make this, you know, kind of, let me go back to them. Where we have them. Where we have the, yes, I mean, this kind of picture. Yeah, because this is a very simple neural network from the one hand, but from the other hand, it's just a nonlinear model, you know, which have a nonlinearity built in, because it's a linear model, nonlinear transformation, linear model. So, and you could see it as a special kind of, you can see this part, G on F of W, as a nonlinear transformation. And afterwards on top, you have just a linear model. So, and with the kind of, with a deep neural network, yes, I mean, like, if you want to see them differently, you could see them differently in this way, but, you know, it's by making a strong differentiation, have we learned too much? I mean, as neural networks are also very good in handling linear functions, you know. You know, kind of like, again, using the same Occam's razor, which I used for the trees. I mean, does it make sense to separate machine learning from the neural networks? I don't think so. Neural networks is a part of machine learning. It's using ideas of machine learning. You know, when the people want to separate that they're doing something special, they're not doing your simple linear models. They say, oh, I'm doing a deep learning, you know, but it's all machine learning.
Okay, whilst people are thinking about questions to ask Prof. Ilya, just a few announcements. Actually, it's one. Today we have our guest talk So lunch will be 45 minutes. So I would like everyone to be back by 18:45 for our guest talk, so that we can proceed with our afternoon session at 2 p.m.
Okay. And you know what I wanted to tell you guys in general, because what I've seen by the questions, sometimes many people are asking for ready recipes, like, oh, what is the optimal number for this? What is the optimal number for that? It depends on your data, and you just need to try. And if something doesn't work, if a certain method doesn't work, you might think, what can you learn from that and try another method. But what you always want to do, you want to use as simple method as possible. Just think about, these neural networks. They sound very cool. They can really, fit the very nonlinear and interesting data. But imagine for a second our discussion yesterday about the kind of using the machine learning tools to give an advices to, I don't know, to the decision makers, why the neural network is taking that some decisions in this direction and that direction is a very serious thing, which, people are doing investigation into that, because, what is a trained neural network? It's a bunch of matrices with some weights. You cannot have such an easy interpretation of why the neural network is thinking, or kind of not thinking, but is predicted that one need to do this behavior or that behavior, or kind of like. So from this point of view, that's why we are also talking about classical machine learning or simple methods, because they are much easier interpretable. They sometimes might seem to be that they're not as powerful as the neural networks, but if you have a not too deep decision tree, you can really literally write it on the piece of paper and say, okay, this is the algorithm of why this algorithm is thinking this or that. And they are much easier and faster to train. And many search engines and very successful search engines are still using, random forest type algorithms or decision tree type algorithms for doing the search or recommendation. So kind of like, you shouldn't think that, that the neural networks are so special. Yes, they're special. They're good in certain classes of tasks, but they have their own problems. Just don't think, yes, that by default you need to go into the neural networks.
Okay, I don't see any more questions in the chat, so I think, okay, there's a question. I'm not sure if Prof, you want to address it now or during the third session.
Okay.
So it's on Slack. They sent a screenshot.
Yeah. Okay. Let's address it in the third session, because yes, it's a tutorial like question. Yeah. So let's speak about that.
Okay. Yeah. Right. So Additional, your question will be addressed during the tutorial session in the afternoon. Otherwise, thank you, Prof, for the session, and thank you everyone for attending.